Welcome to the first online module for this particular semester. This particular module is the Earth and its atmosphere, which is Chapter 1. What I'd like to do is just spend a few minutes talking about some of these topics that you see on the screen here. We'll talk today about the gases in the Earth's atmosphere. Gases will actually play an important role in our atmosphere, and we'll talk about that in the next few chapters. Also in this chapter, we'll look at the vertical structure of the atmosphere in terms of pressure, temperature, and even density. And then we'll look at basically the difference between weather and climate. There is a difference there, and we will just spend a few minutes talking about that. Before we begin, the first thing that we should look at, or the first thing that you're looking at here currently, is the planets in our solar system. You see the sun over on the left side of your screen. The sun is what really dictates weather, and we'll see how specifically in Chapter 2. But the sun emits radiation, as we'll see in Chapter 2, but just to kind of give you an idea here. The sun emits what we call shortwave radiation, and it emits radiation throughout the entire solar system, even some of it making out as far as Neptune and Pluto. But there's about 150 million kilometers separating the sun and the Earth, or about 93 million miles. But the solar radiation is what drives the weather, as we'll see a little bit later. I love this particular picture here. One of the things that should stand out is you begin to see some stratification or layering of the atmosphere. And this particular picture should begin to give you an idea that the atmosphere, the Earth's atmosphere, is made up of different layers, and we'll talk more about those in just a few minutes. But if you'll notice down here at the bottom, these little clouds here, and they're actually not little at all. In fact, this big cloud right here is a thunderstorm. But on this particular perspective, it looks quite small. Let me go ahead and just clean this up a little bit here. But all of the weather that takes place in our atmosphere occurs in the lowest layers of the atmosphere. And we'll actually identify that here in a few moments. But about 99% of the gases in the atmosphere, and this includes water vapor also, only go up to about 18 miles up into the Earth's surface. Most of our weather does occur within the first 10 to 15 kilometers, or you're basically looking about the first 6 to 9 miles up. And the atmosphere, as you'll learn here in a few minutes, extends all the way up almost 300 miles. Here are some of the atmospheric gases. They are subdivided into permanent gases and variable gases. Permanent gases, obviously, such as nitrogen and oxygen, you see make up the largest percentage. Almost 99% of the amount of permanent gases in our atmosphere is made up of nitrogen and oxygen. By percentage, 78% nitrogen, 21% oxygen, and then you have some trace gases here that you see in our atmosphere. Variable gases play a critical role in our weather, especially these two particular variable gases here, water vapor. And all water vapor is just water in the gaseous form. You know, water can exist in three states: solid, liquid, and gas. And water vapor is just water in the gaseous form. CO2, you've heard everything about CO2 in terms of global warming. CO2 actually plays a positive role in our weather, and we'll see how that works also. Ozone occurs up in the upper areas of our atmosphere, specifically the stratosphere, and we'll talk about that. But because of ozone, we are able to be protected from some of the sun's ultraviolet radiation. You know, UV rays can damage our skin, cause sunburns, skin cancer, things like this. Ozone plays a critical role. Probably over the last 20 years, you've heard this idea about the ozone hole over Antarctica. In fact, if you go down to Australia, they have ozone alerts during the afternoon. And so ozone concentrations in that particular part of the world is not nearly as high as it is where we're at. And so they're They have to be careful about wearing protection against the sun. But we'll talk about that also. CFCs, chlorofluorocarbons, which you often find in refrigerants used as a propellant. We used to use that in some of our hairspray cans. Some of you in the audience that's about my age will recall that. We also used to use underarm cans. So the propellant in these produce something called CFCs, which can be extremely damaging to our atmosphere, and we'll talk about why in just a little bit. Notice that the concentration of water vapor, when we say variable, we mean that the concentration of gases tends to vary from time to time. Water vapor down near the Gulf Coast, the tropical regions, can make up as much as 4% by volume. And by the time you get up to the poles, you'll see trace amounts of water vapor. Most of the water up in that particular area up near the poles is in the solid form. And you see here carbon dioxide doesn't look like a whole lot in our atmosphere, but it does make a huge difference. Notice this 374. This is measuring carbon dioxide in terms of parts per million. So 374 parts per million in terms of concentration is made up of carbon dioxide. Why do we care about that? Well, let's take a look at a couple of the graphs here. We have two graphs here. The graph on the left being a look at how CO2 concentration has changed from about 1955 up to 2005. And you'll notice we've got the year down here on the x-axis and the concentration or the amount of CO2, you can think of this. And you see this line up here. This solid blue line is what we call a moving average. It's a trend line. And you see that trend line increasing as we go through the years. In fact, if we look back around 1960, it was about 315 parts per million, and as of 2005, it looks like it's right around 370 parts per million. So we've had a 55 part per million increase in the concentration of CO2. We'll talk about why that has been occurring a little bit later. If we look over here on the right, this graph here, methane. That's gas that often comes from the belching of cows, believe it or not. In rice paddies, you'll find methane being sent off into the atmosphere. And we notice that we measure methane and we can see an increase in that particular gas as we go from 1980 up to 2000. And that's also measured in parts per million. So in these two gases, and by the way, these two gases will be referred to as greenhouse gases, and we'll define what that is a little bit later. But we see that these greenhouse gases, along with nitrous oxides and chlorofluorocarbons, that are increasing in concentrations. And we'll see the role that plays in our weather and the sources for those. Aerosols and pollutants. What if I told you that we could wipe out all pollution in the atmosphere, our air would be perfectly clean? Seems like a good thing, doesn't it? Well, actually what would happen if we had a completely clean atmosphere, it would be very difficult to get any rain. That's right. We need dirty air. Now I use that term loosely, but we need particles in the atmosphere to help precipitation form. And we'll learn about that a little bit later in the semester. But you're seeing a picture here of volcanic ash being shot up into the atmosphere. Those ash particles are basically places where precipitation can begin to form. Soil particles that are thrown up into the atmosphere. Sulfur, nitrogen oxides. All of these types of things can be used to create precipitation. They can also be a cause for problems with breathing and other types of physical ailments. So they play both a positive and negative role in our weather. Okay, let's talk a little bit about pressure and density. What you're looking at here is a graph, and on this particular graph, we see values low to high. Okay, so in this particular case, we're looking at air pressure and air density. So as we go from left to right, we see the values of pressure and density increasing. And then the y-axis is altitude. This altitude is up to about 300 miles up into the atmosphere. So let's start here at the surface, and let's start first of all with pressure. And we see that pressure starts down here and begins to decrease as we go up into the atmosphere. If we go up to about 200 kilometers, we see that the value of air pressure is moving toward the low end. So pressure decreases as we go up into the atmosphere. We also notice that density, air density, also starts off high at the surface, down at 0 kilometers, and as it begins to move up, the density begins to decrease. And so we see that air pressure and density begin to decrease as we go up in the atmosphere. Well, let me go ahead and just clean this up briefly. Notice over here on the right-hand side, there is a column of air molecules. And it's a column of air molecules that start at the surface all the way up to the top of the atmosphere at about 300 miles. And within this column, you'll notice there are a bunch of air molecules. So we've got all these air molecules in this column of the atmosphere. Notice that the concentration of these air molecules tends to be very high. In other words, the distance between these different air parcels or air molecules is smaller than, say, up here. We see there are larger distances between air molecules as we go up into the atmosphere. So it says something about the density of air. As we go up into the atmosphere, it begins to decrease. And in fact, there's an equation for density. It's mass per unit volume. So it's the amount of mass that you have in a particular column. The volume of this column here makes up the density. And so you see that the air is more dense here at the surface than it is up here. If you've ever been to Denver, you talk about the Mile High City, and you've been walking up in the mountains, you'll notice that your breathing becomes much more labored. It's because there's not as many air molecules in Denver than there is here in Iowa. The density of air begins to decrease as you go westward up to Colorado. We also talk about pressure, and pressure is defined as force per unit area. Okay, so what we're talking about here is if we're to look at this particular column of air molecules, and if we were able to weigh or to actually calculate the pressure, it would be how much pressure is being exerted by all of these air molecules on the surface. So pressure is the force exerted, in this particular case, by all of the air molecules in this column over a unit area, which would be the surface of the Earth. That is how we measure pressure. So it's like if you took, for example, if we look at the column of air here, it exerts, in terms of pressure, it exerts 14.7 pounds per every square inch. So if you were to look around at your feet and you look at every square inch, there's about 14.7 pounds of pressure being exerted per square inch because of the number of air molecules in a column of air. We can also measure air pressure in terms of millibars, which you've heard about watching the weather, in terms of millibars, and also inches of mercury. When I was a kid, inches of mercury was the big thing that we used when we were talking about air pressure. This was back in the late 60s, early 70s. You would watch television meteorology and hear about inches of mercury. Now we go with millibars. So let's take a look at the vertical profile of pressure here. As a reference, we have Mount Everest listed here, or shown here. And you see that pressure at the surface is right around 1,000 millibars. Because on the x-axis here we're measuring pressure in millibars, and we're looking at the y-axis being altitude, how high we go up into the atmosphere. And we see that as we go up into the atmosphere, pressure begins to decrease. And in fact, if we go up to about 10 kilometers, the air pressure is about 90 millibars, according to this graph. There's a value of about 10 millibars per 100 meters in terms of how pressure changes over a linear distance. And that applies to about right here, about 10 millibars per 100 meters. But the rate of decrease of pressure begins to get much more rapidly as we go higher up in the atmosphere. We can also look at the vertical profile of the atmosphere in terms of layers. If you recall earlier, let me see if I can find that slide. That was that nice picture that I showed you, this one right here. And again, you could notice all of the different layers. Notice that there are discernible layers here, at least by color. These are all different layers. Remember that the weather occurs in this lower layer. We haven't actually identified that layer yet. And then you'll notice a layer right above that that's very clear. There's a little bit of cloud cover up in that area, but not much. And then you have another darker blue, and then basically out in space here. So we see that there are different layers in the atmosphere. Let's go ahead and just spend a few minutes becoming familiar with these. Now again, we have a graph here of temperature in degrees Celsius and Fahrenheit, and we have the y-axis being altitude, in other words going up into the atmosphere, and you see this goes from 0 to 120 kilometers, which is about 72 miles up into the atmosphere. And we also have it in terms of miles here, you see. So let's go ahead and let's identify the different layers of the atmosphere. In the lowest layer, we've identified this as what we call troposphere. And tropos basically means an overturning of the atmosphere. There's a mixture of the atmosphere, and we'll see that. And then you see the layer above that called the stratosphere. The stratosphere is about from 50 kilometers to about 12 kilometers. So from 12 to 50 kilometers is the stratosphere. In other words, everything's very stratified. There's not a lot of mixing in this particular part of the atmosphere. As we go from the stratosphere up, we have a layer called the mesosphere. And beyond that, the thermosphere, and yet another layer that doesn't show up in this particular area called the exosphere. Let me just clean this up a little bit so we can look at this a little bit more detailed. Also notice at each of the different boundaries of each of the layers we have something called a tropopause, which is the lid over the troposphere, the stratopause, and the mesopause. So in the troposphere, which is where our weather occurs, in the lowest 12 kilometers of the atmosphere, we notice something about temperature. Temperature typically decreases in the troposphere. So as we go from the surface up to about 12 kilometers, on average the temperature begins to decrease. We hit the tropopause, which is the top of the troposphere, and then you notice that temperature really doesn't change a whole bunch. It actually stays about the same. And then it begins to increase again. Now this is in the stratosphere. Now notice something here. We've got ozone maximum. In other words, we've got ozone running around at this part of the atmosphere, O3 molecules. So obviously ozone has something to do with the increase in temperature. And in Chapter 2, we will talk about the relationship between molecular motion and temperature. But I thought I'd just point this out right now. It's kind of interesting that temperature begins to increase right near the ozone maximum. It's not at its highest level, the temperature, but this is where it begins to increase. And then as we go up from the stratopause up into the mesosphere, temperature doesn't change very rapidly. In fact, it stays the same. And then temperature begins to drop again. So what I would like you to do is just spend a few minutes. You might pause your presentation here and just study this particular diagram, convincing yourself that you understand that when the graph is going like this, temperature is decreasing as you go up in height. Temperature in the x-axis, height in the y-axis. So we have 8 different layers here. Layers such as the troposphere, the tropopause, the stratosphere, the stratopause, the mesosphere, the mesopause, the thermosphere, the thermopause, and then we have the exosphere, which is not pictured here. But we're looking at these layers in terms of temperature. That's how we're basically delineating the difference between all of the layers, is by the vertical temperature profile. We can also look at the atmosphere in terms of layers based upon how well or how poorly they are mixed. In other words, if you look at this particular graph, you've got temperature in degrees Celsius, and you see again our temperature profile, temperature decreasing with height, increasing, corresponding to the troposphere. The stratosphere begins to decrease again, begins to decrease, and begins to increase at this point. But we can look at the layer of the atmosphere that I'm drawing about right here. Everything below about 100 kilometers is what we call the homosphere. In other words, the homosphere is a well-mixed region of gases, the concentration being 78% nitrogen, 21% oxygen. Above that is the poorly mixed heterosphere, and some of your heavier gases begin to pool down in the lower portion of the heterosphere, and gases such as hydrogen and helium that are very light begin to move up into this portion. We can also look at the atmosphere in terms of its charged particles, the ionosphere. Let me go ahead and clean this up a bit. Again, we can look at it in terms of the ionosphere, charged particles, which go from about 60 kilometers on up. But typically what we're going to use, we're going to look at the vertical profile of the atmosphere in terms of temperature. We won't look at it in terms of the homosphere, heterosphere, or the ionosphere, but in terms of temperature. But I just thought I would mention this particular figure here to show that we can classify the atmosphere in ways other than temperature. Okay, let's just spend a couple of minutes here as we close out Chapter 1 talking about the differences between weather and climate. A lot of times these particular terms are used interchangeably. Weather is composed of these parameters here, such as temperature, pressure, humidity, clouds, precipitation, visibility, wind. Climate also uses these particular variables when describing components. The difference is climate represents long-term averages. Weather represents phenomena that's happening in the short term. In other words, minutes, days, weeks. But if you want to look at these parameters in terms of long-term averages, then we're talking about climate. Also in meteorology, we use satellites to look at the weather. This particular figure here probably looks very familiar to you if you watch the evening weather. This is what we call a satellite image. And you see all the different clouds. This is the U.S. You see a hurricane down here in the South Pacific. You see clouds up over just east of Iowa when this particular picture was taken. We actually have a satellite that is in synchronous orbit with the Earth that takes pictures during the day and also senses or takes pictures at night. In other words, when you don't have a light source, it can still take pictures, and that's what we call infrared satellite, and we'll learn how that works in the next chapter. You'll also become very familiar with what we call a surface weather map. And basically what a surface weather map is just an area. For instance, if I pick this point up here, let's say down in Nebraska, We see a number here which is 45, which corresponds to the temperature. We see a filled-in dot, which indicates 100% cloud cover. And then we see this line in barb, which indicates wind direction. We'll learn about that a little bit later when we begin working with forecasting. But what these little stations represent is the weather at different spots across the U.S. that I'm marking out. And then on a surface map, you will typically see what we call fronts, this being a cold front, warm front, occluded front. You'll learn all about this a little bit later. L, which stands for low pressure, H stands for high pressure. Typically, we have inclement weather around low pressure, fair weather around high pressure. You're going to learn, like I said, all about this as we go through this semester. But you, along with meteorologists, will use surface weather maps to help represent the weather. As we close out today, there's a very interesting section at the end of this chapter that talks about the history and overview of meteorology. What I'd like you to do is just take a few minutes and read through the pages 17 through 24.